Many people think that the internet is just there and that it always just works. In reality, an enormous amount of infrastructure exists behind the scenes to make the internet just work. In this video, we will use the computer network at the University of South Florida to show you what the internet infrastructure of a modern enterprise looks like and what it takes to keep it running. The network is the foundation on which all USF communications are based. Whether you're using a desktop PC wired to the campus network or a wireless mobile device such as a laptop, tablet, or phone, the network transports your traffic to servers throughout the campus and around the world. You will see USF's network from the desktop all the way to the campus core. We will show you the cabling, switches, routers, and wireless access points that enable high-speed connectivity throughout the university. To help guide you during this tour, we'll first take a look at a high-level network diagram. Because USF's network is made up of nearly 10,000 pieces of equipment, providing connectivity to over 70,000 switchboards and 4,000 wireless access points, it's impossible to include every element in a single graphic. At the top of this diagram, you can see the Tampa campus core. It is made up of two redundant devices which provide 100 gigabit per second and 10 gigabit per second connectivity to the distribution layer devices shown in the middle section. Those distribution layer devices then provide 10 gigabit per second and 1 gigabit per second connectivity to surrounding buildings shown in the bottom section. Within those buildings, there are aggregation devices which provide connectivity to wiring closets. And within those wiring closets, there are devices which connect the individual desktops and wireless access points. Since USF's network is very large and complex, our tour will focus on the connectivity to one specific desktop. This desktop is located in the computing lab in the ISA building. This diagram shows a simplified view of the network. The same core, distribution, and access layers are shown, but we are just looking at the network devices which connect that one PC. We'll start our tour at the access layer or edge of the network. It is here that desktops, both wired and wireless, connect. Most desktops at USF are connected over Category 5E or Category 6 copper cabling. You can see that this desktop has a patch cord running from its Ethernet network interface card to a nearby wall jack. The cabling for this wall jack runs through the ceiling back to a wiring closet. We call this room an Intermediate Distribution Frame, or IDF. This room serves as an aggregation point for all of the copper cabling from desktops in the surrounding area. IDFs can serve desktops on the same or different floors. Most versions of Ethernet are limited to distances of 100 meters over copper cabling. So it's important to position these IDFs so that the maximum cabling distance isn't exceeded. We will now look at the IDF servicing our example desktop. This room houses Ethernet switches that connect to all of the copper cabling from the various desktops and access points in the area. The cabling is terminated onto patch panels in a rack, and patch cords are used to connect those jacks to the switches also located in the rack. Terminating the cabling on patch panels allows for easy replacement of network equipment as new technologies become available. If we ran the cabling directly to the equipment, not only would cable management be difficult, but the cabling might not reach as new equipment was installed. Each stack of switches is redundantly uplinked to separate building aggregation switches. Looking at our simplified network diagram, you can see that the top and bottom switches in this stack have fiber-optic connections going to different building aggregation switches. Typically, we design the primary uplink to run at 10 gigabit per second and the secondary link to run at 1 gigabits per second. This helps reduce cost while still maintaining redundancy. The fiber connections from these switches run to fiber patch panels very similar to the ones you've seen for copper cabling. This fiber runs from the IDF to the Building Distribution Frame, or BDF. The BDF serves as an aggregation point for all of the building fiber, and it houses the network equipment which connects all of that fiber. Before leaving this IDF, we should discuss some environmental requirements of the room. Network equipment generates a certain amount of heat, so it's important when designing a wiring closet that we make sure sufficient air conditioning will be provided. We must also be able to continue running the network for at least some period of time during a power outage. This means that we must install uninterruptible power supplies, UPSs, to provide power to our IDF equipment. In buildings utilizing voice over IP for telephony, we are required by university policy to run the network for at least 90 minutes during a power failure. This allows phones to continue operating for emergency calls. Many of our buildings have backup generators that will automatically start after power has failed. But we still need UPSs to get us through the brief outage while these generators start. Now we will look at the BDF upstream from the IDF we just visited. The fiber optic cabling you saw in the IDF runs through the ceiling and often through conduit to the BDF. When it arrives in the BDF, it is terminated on patch panels just like you saw previously. From here, fiber patch cords connect to the building aggregation switches. As you can see, there are two aggregation switches in this BDF. One provides 10 gigabit per second connectivity, and the other provides 1 gigabit per second connectivity to the downstream IDFs. The speed of the ports are determined by the installed optical modules. These optics commonly used today are called SFPs, small form factor pluggables. As you can see in our simplified network diagram, we have moved from the desktop to the desktop aggregation to the building aggregation point, but we're still in the access layer. From here, our building aggregation switches uplink via fiber to the equipment in our distribution layer. These fiber optic connections leave the building and run underground to what USF calls a distribution node. These nodes serve as aggregation points for fiber to surrounding buildings. As of 2013, USF has 6 distribution nodes to meet the computer networking needs of its entire campus of approximately 1 square mile. The fiber patch cords you've seen so far have been orange or aqua in color. This typically signifies multi-mode fiber. However, if you look at the building aggregation switches in our BDF, you'll also see a yellow cable connecting to each. This is the single-mode uplink leaving the building. The jacket you see around fiber is there to protect it from day-to-day handling. Fiber-optic cabling is basically just a very thin piece of glass through which light is sent. This glass must be carefully protected. If you strip back the jacket of these fibers, you will see a smaller cable inside. And if you remove the plastic that covers this smaller cable, you'll see the tiny strand of glass that is the fiber-optic cable. That strand of glass is capable of sending hundreds of gigabits per second of information over tens of kilometers, but it is also extremely fragile. We'll now visit the campus distribution node, which services as an aggregation point for surrounding buildings. You can see the fiber coming into this node through conduits that are installed on its outer wall. Each of those smaller black cables contains tens to hundreds of individual fiber strands. As with the IDFs and BDFs, these strands are terminated on fiber patch panels, and patch cords are used to connect them to the network equipment in the node. Each rack you see here houses fiber from a few dozen surrounding buildings. Since the distribution node serves many buildings, a failure at this node can affect network connectivity for users in all these buildings. It therefore makes economic sense to provide a high level of redundancy at this node. Accordingly, this node has redundant distribution layer devices. At USF, these are Cisco 6500s and Cisco Nexus 7000s. They are a combination of a switch and a router. They route traffic between different subnets and switch that traffic out to the surrounding buildings. The fiber optic cables you see plugged into these devices connect to the building distribution switches that we just saw in the BDF. They typically run a few thousand meters underground from that BDF to this distribution layer device. Looking again at the simplified network diagram, you see that each distribution layer device is uplinked to both core devices. These uplinks run at speeds between 10 gigabits per second and 100 gigabits per second, depending on the bandwidth demands of a particular node. These links also use the same single-mode fiber that we use from the buildings to the distribution nodes. All devices we use at USF's distribution layer have redundant power supplies and, where possible, redundant forwarding hardware. The node itself has a dedicated generator, and UPS capable of running the room for at least 4 hours in the event of a power failure, including if the generator doesn't start, and sufficient redundant cooling to keep the room at around 72 degrees even if all but one of the air conditioning units fail. From the distribution layer, we move up into the campus core. The Tampa campus backbone is made up of 2 redundant Cisco Nexus 7000 devices. In fact, the core equipment is basically identical to the distribution layer equipment. The core equipment simply aggregates distribution layer devices like the distribution layer aggregates buildings. Looking back at the more detailed network diagram, you can see how the 2 core devices connect together each of the distribution layer devices, and you can see the path that we've been following from the desktop up to the core. This path is replicated for the tens of thousands of devices connecting to USF's network. But the design is fairly simple. Desktop wiring closets aggregate to the building wiring closet, buildings aggregate to distribution nodes, and the distribution nodes are networked together by the core devices. At this point, you might be asking yourself how the routers in USF's distribution and core layers figure out where to forward the traffic they receive. This routing decision is accomplished by building a table of reachable networks and where traffic should be forwarded next to reach those networks. This table is built automatically using a routing protocol called OSPF, or Open Shortest Path First. This protocol is run by all of the routers in USF's network. It defines how those routers should exchange network reachability information, and it tells those routers how they should build their routing table so that they have a loop-free best path route to all networks. For example, here is a route to the network 10.220.60.0/22. As you can see, the routing protocol tells us that this network is reachable via the next hop of 131.247.254.34. We have hundreds of these routes in our network. So far, we've focused on how a desktop is connected to the USF network, but just having a desktop on the network isn't useful unless it's able to communicate with other devices like servers and other clients. After all, the point of networking is to enable communications. So we'll now look at how traffic gets to the internet once it reaches USF's campus core. Looking again at the high-level network diagram, you can see that there are a pair of WAN routers connected to the backbone switches. These devices, WAN 1 and WAN 2, provide wide area connectivity to USF's internet service providers. WAN 1 is a Cisco ASR 9006 and WAN 2 is a Cisco 7600. USF obtains internet connectivity through Cogent, Time Warner Telecom, and Florida Lambda Rail. These links are delivered to USF as Ethernet connections over single-mode fiber. This is the same kind of Ethernet we've used everywhere along the path from our example desktop. Traffic is routed to the WAN routers by the campus backbone, and those routers determine the best ISP to use for reaching the traffic's destination IP. In order to make this decision, the WAN routers run BGP, or Border Gateway Protocol. There are currently approximately 450,000 routes advertised to USF from our ISPs. Once traffic is forwarded to the appropriate ISP, routers in their network and many other networks beyond that ISP deliver the traffic to its destination. When that remote server responds and sends traffic back to the desktop at USF, the same BGP routing tables guide the traffic through the internet back to USF, and our network delivers it back to that machine. We will now look at the network connectivity to the servers USF runs in its data centers. These data centers host all of USF's business data and applications such as student assignments, grades, email, websites, employee payroll, billing, travel, etc. To ensure continuous service, USF maintains multiple copies of its data. USF houses a primary data center on the Tampa campus, a secondary data center in Winter Haven, and a disaster recovery data center at Clemson University in South Carolina. The Tampa data center is directly connected to the campus core as shown in the high-level network diagram. Two Cisco 6500s provide connectivity to all of the servers and devices in that data center. Individual servers within the data center are connected at 1 gigabits per second and 10 gigabits per second speeds. These servers connect to access layer switches which connect to the 6500s. Really, the network gear in the data center isn't that much different than the equipment you see connecting desktops in buildings. For example, all switches providing connectivity to the servers have dual power supplies connected to different electrical circuits. All critical servers have network connections to 2 different switches, so that if a switch failure does happen, the server can send traffic through its other switch. Each switch is uplinked to different Cisco 6500s, so that if one of those 6500s fail, connectivity would continue through the other one. With nearly 10,000 devices making up USF's network, failures are inevitable. So the network engineering group runs software to monitor every one of these devices. We check their availability and health every 3 minutes. We check things like CPU, memory utilization, optical power levels on the fiber links, room temperatures, UPS capacity, and general functionality of the device. If any of these parameters are out of normal values, we are notified and someone from the operations or engineering group will troubleshoot the issue. We also monitor various statistics from our network gear. We graph input and output traffic levels for every switch port and router port, concurrent users and throughput on every wireless access point, network performance statistics across our backbone and inter-campus WAN links, and call volumes on our telephony systems. Basically, we monitor as much information as we possibly can and attend to any unusual observations. These statistics help us with capacity planning, troubleshooting, and even security. For networks the size of USF's to function, the equipment used in them must be reliable, secure, feature-rich, remotely manageable, and have an assurance of technical support from the manufacturer. It must be what's referred to in the industry as enterprise-class gear. Equipment from vendors like Linksys, D-Link, and Belkin is typically SOHO class, small office or home office class gear. These low-end devices work well in the home or in a small office that's not part of a larger enterprise network. They have many useful features that work in that environment. For example, they are inexpensive and usually require no configuration and are ready to run out of the box. When they fail, they just need to be replaced with similar equipment. For an office with 5 to 10 users, this is adequate, but they do not do well in a large network like we have here at USF. USF needs many high-end features not available in SOHO class gear, and we need the ability to remotely monitor and manage all aspects of each network device. Enterprise-class equipment is certainly more expensive than Soho gear, but that extra cost helps guarantee the networks we build provide the level of service our users demand. They are capable of handling heavy traffic loads from thousands of users. Their remote administration and configuration features allow a small group of network experts to manage thousands of devices. Their configurability allows USF to respond to changes in network needs by reconfiguring traffic routes as appropriate. The entire USF network of nearly 10,000 devices is managed and operated by a small group of experts. 5 engineers design and support all of the networks and services. 4 network operations staff handle tasks such as equipment configuration and installation. We also have several staff maintaining the physical cabling, handling requests from users for adds, moves, and changes, and we have a team who handles telephony for the campus. You have seen USF's network from the desktop all the way up to the campus core and out to the internet. You've seen how traffic gets to the internet and how the infrastructure in USF's primary data center is designed. We've discussed how all of this infrastructure is monitored and what kinds of network gear are required for an enterprise-class network. I could literally spend hours talking about any one of the topics we've covered in this video, but hopefully this short introduction has provided you a good understanding of the technologies which make up USF's network. The network of any large enterprise will share many of the similarities with this network, and if you find these technologies as interesting as I do, I hope this has encouraged you to continue learning about them and perhaps even consider working on them.